Hello everyone, this is the second part of our series to generate the exact solution of a second order ODE. In this video specifically we solve the example to reinforce the computation of the constants associated with the homogeneous solution and particular solution. So here we have a second order differential equation and we are given the initial condition for y and y prime, and we would like to generate the exact solution y of t. We know that the exact solution has two components, a homogeneous part and a particular part. The homogeneous part depends on the roots of the characteristic polynomial and it will have an exponential form. The particular part depends on the right hand side of this equation, which is a sinusoid, so we expect that the particular solution will also be a sinusoid according to the schedule presented at the previous lecture. So let's start with the homogeneous solution. So to get the homogeneous solution we have to construct our characteristic polynomial. So we are going to replace the second derivative by s squared, and the coefficient of the second derivative was 2. We are going to replace the first derivative by s, and the coefficient of the first derivative was 3, and the linear term y, we just write the coefficient associated with it, and we set the right hand side to 0. Now we get the roots of this equation, roots of s, and based on the root distribution we have one of three possibilities for the homogeneous solution. Okay, so the two roots alpha 1 and alpha 2 can be obtained as minus 3 plus or minus 3 squared minus 4 times 2 times 3.125 divided by 2 times 2, and this gives us a complex number whose value is minus 0.75 plus or minus j1. So now you can see that our two roots are complex conjugate pairs. The real part is minus 0.75, the imaginary part is 1. So now we have this nominal form associated to complex conjugate pool or root. So the homogeneous solution is equal to e minus alpha times k1 cosine beta plus k2 sine beta, where alpha and beta are the real and imaginary part of the two roots. So this is equal to e minus 0.75, I forgot a t here, t k1 cosine beta was equal to 1, so it'd be cosine t plus k2 sine beta t, beta is equal to 1. Okay, so this is our homogeneous solution. We have k1 and k2, there are two unknowns, and we are going to use the provided values of the two initial conditions to solve for them once we have the form of the complete solution. So for the particular solution should take similar form to the right hand side of the differential equation. So here we have a sinusoid, and therefore the proposed particular solution should also be a sinusoid. According to the table from the previous slide, it would be a sine t. It should be a sinusoid of the same frequency, but now we have a sine and a cosine, a superposition of sine and cosine. Now a and p are two constants. They are unknown right now, and we need to solve for them. The way to solve for them is to substitute this proposed solution for the particular part into the differential equation and solve for the value of a and p that make that equality hold. So now we need to compute the first derivative with respect to time. So from here is equal to a cosine t minus b sine t. So here we have an expression for the first derivative. We do the same for the second derivative. So we need to compute the second derivative so that we can substitute the second derivative expression into the differential equation. So the second derivative is the first derivative of the first derivative. So this is equal to minus a sine t minus b cosine t. Now I have the proposed yp, I have the derivative, substitute yp and its derivative into that differential equation and solve for a and p that make that equation hold. So let's do the substitution together. So we have 2 times the second derivative. So the second derivative is minus a sine t minus b cosine t, and then plus 3 times the first derivative. So that is a cosine t minus b sine t, and then we have plus 3.125 y, so it is a sine t plus b sine t. So this part here is the second derivative, this part here is the first derivative, this part here is yp, and then the right hand side was simply sine t. So now you can see that the left hand side has sinusoids, sines and cosines. So let's combine the coefficients that belong to a sine and belong the coefficients that belongs to a cosine. So here we have a sine here, and I made a typo. This should be a cosine. Okay, so adding up the coefficient of the sine function, I have 1.125a minus 3b. Those are the coefficient of sine t. And then I do the same for the cosine function. So I have a cosine here, a cosine here, and a cosine here. So add these coefficients together. This would give me 1.125b plus 3a times, so let me rewrite it onto a different line. So it would be 1.125b plus 3a cosine t. So this is how I combine the left hand side of that equation. The sine component has a cosine component. Then the right hand side is equal to sine t. Now for the equality to hold, I have to choose the value of a and b to satisfy that equation. Now you can see that on the left hand side we have a cosine, but on the right hand side we don't have any cosine. So this suggests that this term has to be equal to 0 such that this equation holds. So I have 1.125b plus 3a, which is the coefficient of cosine of the left hand side, should equal to 0 because we don't have any cosine on the right hand side. This is the first equation in the two unknowns a and b. The second equation that we have is that we compare the coefficient of the sine. So on the right hand side the coefficient of sine is 1, and on the left hand side this is the coefficient of the sine. For equality to hold, we need this boxed expression to equal to 1. So this gives us 1.125a minus 3b has to equal to 1. And this is the second equation in the two unknowns a and b. So now we have two equations in two unknowns. We can solve simultaneously for a and b. And the solution for that is a equals to 0.109 and b is equal to minus 0.292. So now we can complete our particular solution. Yp equals to 0.109 sine t minus 0.292 cosine t. So now we have an expression for the homogeneous part, we have an expression for the particular part, you combine them together for the exact solution. So this is equal to e minus 0.75 t k1 cosine t plus k2 sine t, this is the homogeneous part, plus 0.109 sine t minus 0.292 cosine t. Okay, so this gives us the exact solution. However, we still have these two unknowns k1 and k2, which are the constant corresponding to the homogeneous solution. What we do now is that we use the initial conditions, apply them into that exact solution to solve for k1 and k2. We have two values for the initial condition. So we have y of 0 equal to 5, and we have dy dt when t is equal to 0 equals to 3. So from the expressions that we have for y, we substitute every t equal to 0. So we have 5 equals to e minus 0.75 times t is equal to 0 times k1 cosine 0 plus k2 sine 0 plus 0.109 sine 0 minus 0.292 cosine 0. So I use the expressions that I have for the exact solution. I substitute every t by 0 and equate to 5. So now you can see that this term cancels. This is 0, this is 0, and we can immediately solve for k1. So I have on the left hand side 5, this is 1 times k1 minus 0.292. From here we have k1 equals to 5.292. So this is the first coefficient that we have. Now we need to get the derivative dy dt so that we can use the second initial condition. Okay, so we already have an expression for y of t. We take the derivative dy dt is equal to minus 0.75 e minus 0.75 t k1 cosine t plus k2 sine t plus e minus 0.75 t minus k1 sine t plus k2 cosine t. So this is the derivative of the homogeneous part, and then we take the derivative of the particular part. It will give us 0.109 cosine t plus 0.292 sine t. So this part here is the derivative of the particular part. Now we use the initial condition dy dt when t is equal to 0. It was given to us as 3. So in this expression for the derivative, we substitute every t equal to 0. So we have minus 0.75 e to the minus 0 times k1 cosine 0 plus k2 sine 0 plus e to the power 0 minus k1 sine 0 plus k2 cosine 0 plus 0.109 cosine 0 plus 0.292 sine 0. So now this is an equation. We have the values of the sines of cosines. We already solved for k1 in the previous step, so the only unknown in this equation is k2. So let's just clean up this equation. It will give us 3 on the left hand side, and from our expression we have minus 0.75 k1 plus k2 plus 0.109. We already know k1 from the previous step, so substitute the values that we have for k1. So we get 3 equal to minus 0.75 times 5.529 plus k2 plus 0.109. The only unknown here is k2, and this gives us k2 equals to 6.859. So now we have a solution for k1 and k2. Then the complete solution can be given as follow. We already had this expression. The only missing part was k1 and k2. We solved for them, so we add them here. So it is e minus 0.75 t times k1, 5.29 times cosine t plus k2, which is 6.859 sine t. So this completes the homogeneous solution plus the particular solution, which was 0.109 sine t plus negative 0.292 cosine t. So this is the complete solution after solving for all the unknowns, and this completes the solution for this problem. Thank you.